Determine the graph of the derivative function given the graph of a polynomial function. Alright, so in this video we're going to be talking about graphs of functions and then their graphs of their derivatives. So to do that, we're going to look at a particular function, f of x is equal to x squared plus x minus 2, and we're going to use a table here to actually graph the function. We are then going to look at the derivative, f prime of x equals 2x plus 1, and we're going to use the information from the first graph to then graph the derivative and fill in the table. Alright, so let's go ahead and let's get started here. So in our first table here, we're told that x equals 2. When we plug 2 into our function, we're going to end up with 0. Which means that on our graph, we're going to plot the point -2, 0. Then with the x value, the next one is -1. When we throw that into our function, we're going to get an output of -2, giving us the ordered pair of -1, -2. Next up, when we throw -0.5 into our function, we get -2.25 as our output, which is going to be somewhere right around there on our graph. Then when we plug 0 into our function, we're going to get an output of -2. So we can come in and we can plot that point. When we plug in x equals 1, we're going to get 0. And then when we plug in x equals 2, we are going to get 4. Alright, now looking at this graph, we can go ahead and we can connect the dots, and as we can expect by looking at the function, we can see that this is a quadratic equation, which is going to form a parabola, even though that's not necessarily what the shape I just drew looks like. Alright, so we can now use the graph of x squared plus x minus 2 to figure out what the graph of its derivative will look like. Now remember, the derivative represents the slope at specific points. So in order to graph the derivative, we need to figure out the slope at some points on our function, specifically the ones that we know. So we're going to go through and we're going to find the slopes at these 6 points. So now to do that, we would actually go through and we would draw the tangent line. So let's go ahead and let's just sketch some tangent lines. So these would be roughly what the tangent lines are. So there's the tangent line through the point -2. And again, this is just a sketch of the graph. But due to some behind-the-scenes stuff, I will tell you that the slope of this particular tangent line is -3. So that means at x equals 2, the slope is going to be -3. Or on the derivative graph, we're going to plot the point, that's a -2. We're going to plot the point -2, -3. Because -2 is the x value, and then the output of the derivative is the slope. Then we can come in and we can do the same thing for our second point at x equals 1. And we can come in and we can draw the tangent line. And again, due to some behind-the-scenes work, we can see that this slope is -1. So at the value x equals -1, the slope will be -1. So now we can plot that point on our derivative graph, -1, -1. And we can continue doing this for the next point, x equals -1/2. And I missed that point a little bit, so we'll just move that up. There we go, now we're good. And this is a tangent line at a turning point, which we know is going to have a slope of 0. And this is going to be at -1/2, 0. And then we can continue drawing tangent lines, but for the sake of time, I'm just going to come in and plot the points. So when x equals 0, the slope is going to be 1. When x equals 1, the slope is going to be 3. And then when x equals 2, the slope is going to be 5. And if we connect the dots here, we can see that we're going to get a linear line. All right, so now let's just discuss this a little bit. And let's come back over here and let's look at x equals 2. Now we know the input is x equals 2, and based on our table, we can see the output should be 4. And that 4 is going to represent this distance right here. And this distance right here, y equals 4, represents the height of our function f of x at x equals 2. Now, if we move to the derivative graph and we look at that same point, in our derivative graph, this particular distance, our output or our y value, tells us that the slope of the tangent line at x equals 2 is 5, because again, that's the output. This is 0.25. And this is really, it's a difficult concept, because when we're used to graphing functions, usually the y value represents the height of the function, and that's the only meaning. Well, now when we graph its derivative, the height now represents something else. The height now represents the slope. So again, this vertical axis here is going to be the slope of f of x. Again, that's a really tricky concept to wrap your head around. It's not one that we're used to doing, but hopefully when we look at a few examples, it'll start to come to us. Now, if we go back up to the table, f prime of x equals 2x plus 1, we can always plug in our x values into the function, and if we do, you'll notice we'll get the same outputs. So if we plug x equals negative 2 into our derivative, we'll get an output of negative 3, which tells us the slope at x equals negative 2 is negative 3. If we were to plug in negative 1, we get negative 1, and then 0, 1, 3, and 5. And again, all those points confirm the slopes, and all those derivatives are the slopes at their respective x values. Last thing I want to mention here is notice how, when we took the derivative, we started out with a quadratic, and we ended up with a linear function. Whenever we take the derivative of a function, we always go down, or we always lower it by 1 degree. Let me rephrase that. Whenever we take the derivative of a polynomial function, it always gets lowered by 1 degree. So a quadratic becomes linear. A cubic will come quadratic, and so on and so forth. And this is something we'll explore later on, but I just wanted to help make that connection now. All right, next up, we're actually going to start sketching some graphs of these things. So I just wanted to quickly review what certain components of graphs represent. So for example, in the graph of f of x, a positive y value means that the graph is going to be above the x-axis, which makes sense. A positive output is above the x-axis, which is 0. A negative y value means that our graph is going to be below the x-axis. And then a y value that's 0, aka an x-intercept, will be on the x-axis. Again, this is all stuff that we know from previous math classes. However, it's important to review this because when we start talking about graphs of derivatives, these things are going to mean something different. So, for graphs of f prime, if our function, meaning the original function, has a positive slope, that means the graph of our derivative is going to be above the x-axis. Because again, slope is the output, and since it's positive, it needs to be above the x-axis. Then, if the slope of the original function is negative, that means our derivative graph is going to be below the x-axis. And then finally, if we have a slope of 0, a slope of 0 means the graph is going to be on the x-axis, or it's going to be an x-intercept of our derivative function. So again, whenever we're graphing f prime of x, the output is going to be the slope of the original function. So let's take a look at how this works. So we want to sketch the derivative of the following graph, and we're given a graph. It looks like it's going to be a, what's that going to be? A polynomial to the fourth root because it has 3 turning points. So now how do we start off by sketching this? Well, first we want to identify the turning points. So we'll come in here, we can see we're going to have a turning point at x equals, what, negative 1.5, a turning point here at 2, and a turning point here at 4. Now, why is it important to identify those turning points first? Well, the reason it's important is because, remember, we said turning points mean that there is a horizontal tangent line at these values, which means at each of these x values, the slope is going to be 0. So we can start off by plotting those points on our graph of the derivative. So we know that when x equals negative 1.5, the slope is going to be 0. So we can put an x-intercept there for our derivative graph. When x equals 2, the slope is also going to be 0. So therefore, on the derivative graph, we have to get another x-axis. And then same thing for x equals 4. All right, great. So those are plotted. Next up, we're going to divide our function up into increasing or decreasing intervals, or positive slope or negative slope. We can see here that for our first piece, we're going to get a negative slope. For the second piece, we're going to get a positive slope. Third piece then is negative, and the fourth piece is positive. So that means for our derivative graph, when the slope is negative, that means that the first portion of our derivative graph will have to live down here. For the second piece, we see it's positive, so for the second piece, we're going to have to live up in this area. The third piece is negative, so we'll have to live below the x-axis somewhere in here. And then for our final piece, it's positive, meaning that that piece of the function will have to live in this area right here. So now let's see how that works. Now, we're given a polynomial, and with the polynomial, we know that the slope changes everywhere. And if we look at our first negative piece over here, we can see that our slope starts out pretty steep. But it starts out pretty steep with a negative slope. So I'm going to denote that with a very big minus sign, because the slope here is very steep. Well, as we approach our turning point, we can see that our slope gets smaller and lessen and smaller and lessen until it gets to 0, which means our slope is the least negative, or the smallest negative, right at the turning point. So I'm going to put a really tiny negative sign there. So as we go from the big to the little sign, we are just going to decrease in slope value. So I'm just going to keep putting smaller and smaller and smaller and smaller negative to indicate that we're going to be getting closer and closer to a slope of 0. Now, how does that look on our derivative graph? Well, a larger negative slope is going to be further away from the x-axis. So that means we're probably going to be somewhere down around here. And again, as we get closer and closer and closer to the turning points, our slope is getting less and less negative, or closer and closer to 0. So does our derivative graph. So since we are just sketching, we're not actually graphing, so this is just a sketch or representation of what it could be, we could say that this particular piece of our derivative graph is going to look like so. All right, moving on to the next piece. We can see that we're starting at a turning point and the slope is 0. So that means we're going to start increasing or having a very itty-bitty positive slope. So a little plus sign. Well, then at the end of this interval, you can see that we're back at 0, so we're going to have another itty-bitty plus sign. But if we look in the middle, if we look kind of right around here at x equals 2, we can see that that is the steepest part of this particular section. So we're going to put a really big plus sign there to say that that is the most positive part, or the biggest positive part, of our increase here. So that needs to be the highest point of our derivative graph. And then in between, that just means we get bigger and bigger till the biggest, and then we get smaller and smaller. So what does that look like? Well, this particular positive interval, we see that we need to start right here, but we also need to end up back down here at the next turning point. And we can see that after the turning point, we're going to increase until we get to the maximum value. And then we're still going to be increasing, but we're just increasing. Oh, that was a bad. Let's try this again. Increase till we get to the top. And then we still increase, but we're increasing less and less until we're stopped increasing at all, back down to 0. Well, then we can keep repeating this process. In this next little portion, we're going to start off with a really tiny decrease and end up with a really tiny decrease. But somewhere in the middle, there's a big decrease. And then medium size in between. So again, looking at that portion on the graph of our derivative function, we need to start here and we need to end up here. And in between the starting and the ending point, we are going to be increasing more. Well, actually, we're going to be decreasing more, which means we're getting farther away from the x-axis. So, whoop, until we reach our most decreasing spot. And then we're still decreasing, but just less and less. And then finally, our last positive piece. Since we're starting at 0, we're going to start at a very little bit increase, but then eventually we're going to end up at a really big increase. So we're just going to casually get larger and larger and larger. And that's what's going to happen with the last piece of our derivative graph. We're going to, the increase, or the amount of slope, positive slope, is going to increase forever and ever and ever, giving us a rough, and again, very rough sketch of what the derivative graph will look like. And going back to what we had talked about at the beginning, the graph we were given was a 4th degree polynomial because it has 3 turning points. Our derivative graph is a cubic function because it only has 2 turning points. So again, we dropped a degree. So let's take a look at one more example. So again, we want to sketch the derivative given the following graph. So first thing we do is we want to identify the turning points. So boom, and boom, and boom. So those are great. Those are where our derivative is going to equal 0. So now we can just plot those x values on our derivative graph because we know those will become x-intercepts. However, in this particular graph, we have another point that has a horizontal tangent line. And that would be this horizontal piece of our polynomial here. So that will also be an x-intercept. All right, then we're going to do the same thing as we did before. Let's see, our first piece is going to have a positive slope. Our next piece is going to be negative. The third piece is going to be positive. And then the fourth piece is still going to be positive. We just took a brief pause there at x equals 2. And then we're just going to come down negative slope. All right, so starting with the leftmost piece, we're going to have a really big positive slope here, but we're going to be climbing up to where the slope is 0, so we're going to end up with an itty-bitty slope. So we can go from a lot of increasing to less increasing to less increasing to less increasing, but still increasing. So therefore, our particular piece of this graph is going to look something like so. Next piece, we start out close to 0 and we end close to 0. So we're going to have 2 itty-bitty negatives there, but somewhere in the middle it's going to be decreasing at a really large amount. So then we're just going to increase a little bit, increase more, get to the max, it's the max increase of the negative slope, and then less and less and less. So that particular graph is going to look something like so. All right, next up, we're increasing a little bit, and then halfway through we'll be increasing the most, but then we're going to get back down to 0 again. So again, we're casually increasing, largest ever, and then less and less of an increase. All right, so that means we're going to look something like so on our derivative graph. All right, well then the next piece, we're going to start at 0, and we're going to end up close to 0, and we're going to be at the biggest increase somewhere in the middle, so bigger and bigger, smaller and smaller. So this is going to look a little funny because we still have a positive slope. So that means we still need to stay up here. So this particular graph is just going to kind of do a loopy-loop, a little M. It's going to come down, it's going to kiss the graph at x equals 2, and then go back up and be positive. And then finally we can see our last piece is going to start out real little, and then get really big, and then just casually get larger and larger and larger, meaning we go down forever and ever and ever. And there you have it. That is a sketch of the derivative function. And that is it, folks. That is determining the graph of the derivative function given the graph of a polynomial function.